Okay. Okay. Yes. Yeah, it's my.
Namaskar and good afternoon to all of you. My name is Atmanandmaya. I am from Indian Institute of Science, Bangalore. I am pursuing a PhD in Interdisciplinary Center of Energy Research. For today's topic, for my research work is analysis and application of Peltier module for the surface temperature measurement in hybrid source thermal desalination unit by module parameter estimation. For today's presentation, this will be the outline. Before going to the introduction, I will just give the highlight of my research work. And highlight of research work about what is the main finding of in this work. The main finding is about the innovative measurement technique. That is, I'm using a non-invasive measurement technique using the Peltier model for surface temperature measurement in the developed desalination unit. And another thing is the parameter estimation of the Peltier module, because the manufacturer is not revealing the material aspects of the Peltier model. I'm trying to extract that parameter for the Peltier module. And again, is the improved system monitoring and control for the desalination process. Novelty of my work lies in the parameter estimation methodology, where I'm extracting the external Seebeck coefficient and the internal Seebeck coefficient in terms of the terminal characteristics of the Peltier module, which finds a unique application in the developed desalination unit. And this will impact in enhancing the system and improving the system reliability by monitoring and controlling the system process. And my work will find a relevance in the advancement in thermal management directly, and directly we can implement this modeling for the practical implementation in the industry. Now comes the what is hybrid source thermal desalination system. As the previous talk by the Professor V on the keynote talk, he was asking about the membrane-based desalination system. I'm just telling you about thermal desalination system where the energy is a thermal. But the thing is, it is hybrid source where I'm using both thermal energy and electrical energy, where the thermal energy I'm mimicking by using a heater, and this electrical energy I'm getting for the photovoltaic thermal. This electrical energy through the DC-DC converter I'm giving to the Peltier module, as DC-DC converter is required because the Peltier because the photovoltaic thermal photovoltaics are intermittent source. It is not a constant source kind of things, and it is integrated for utilizing the latent heat from the condensation chamber to again feed back to the condensation evaporation chamber, so that we can get a closed loop operation of the latent heat, so that we get a very high efficiency. This is replicated in this experimental setup. From this schematic, I designed my own experimental setup to verify that things that what I designed is properly according to the models. And in this setups, I am using the thermal module. It says that it's working at very low temperature difference, so that I can achieve the highest possible coefficient of performance. The thing is, what I leads to again for measurement in the desalination system is that our requirement was the minimum temperature difference, as I can use the Peltier module as a heat pump when there is a temperature difference is low. It can work at a coefficient performance of theoretically very high, but practically I achieved up to 8. So this is the requirement. But the thing is, when I was designing my setup, I forget to give the measurement part for the surface one. Again, if because the Peltier module is mounted and fixed it, if I going for the another measurement kind of things like again inserting another wire, I'm getting a heat loss. Therefore, I need a non-invasive technique like which is already integrated in the system, and I need to measure from that. Therefore, after that, I started finding means if anything is that, so that I can use the Peltier module as a heat pump and again as a temperature sensing element. What I found that in the literature, there is a cap that they are working only for the open circuit voltage. That is, it's not during the process I can do the measurement also, and they do not account for the complexity of the internal dynamics, because in the Peltier model there is internal temperature difference happening and the external temperature difference happening, both of the things. And I already explained this parasitic thermal resistance and the load current, they are not also considering in the thing, which lead to inaccuracy in the parameter extraction. Therefore, we need a more accurate representation of thermoelectric module, which is under condition. That is the loading concept. We are taking the power from the thermoelectric as well. This gives me the problem statement to find the internal temperature difference of the Peltier module based on the measurable parameter like our voltage and current, so that I can practically measure it and compare with the modeling part. Now, this comes a how and why. Now, is that how I can integrate into the system and I do the things. Therefore, before going that, I'll just explain the geometry of this Peltier model. This is the physical interconnect of the Peltier model, where this is the P-type material, this is N-type material, where P-type and N-type material is connected with the copper wires. And above that, it is the hot ceramic surface, and because two ceramic surfaces are there to give a mechanical support to them. And if we give the temperature difference, hot ceramic surface and cold ceramic surface, we'll get a voltage. This is the working kind of things, working principle. And if you zoom in this small legs, you will see that this this is the internal characteristics you can, this part is revealing, and this is the thermal network for that, where I have considered this for the hot ceramic surface, this is for the cold ceramic surface, and this is for the material. But the thing is, both current is flowing and heat is also flowing. I need to have a couple network, and this is the couple network for this Peltier module. Now comes the part with how the integration of my Peltier module with this developed desalination system. This is the cut section view of the habit source and of the Peltier model, where I was placing this Peltier assembly in between these two heatsink, upper heatsink and lower heatsink made of aluminum, and to ensure the thermal coupling base for the experimental setup, I need a thermal adhesive, and another things I need a tightly to board it so that more accurate measurement for the surface we can get it. And right side is the thermal network for the whole systems, considering the one-dimensional analysis. In this thermal network, I need to have a measurable point where I can measure things, and again I can tell that if the measurable point is there, I get this modeling is going to give a correct result. This THS and TSS is the heatsink part, and TH and TC are the external part, which is the ceramic substrate part, and TH and TC are the temperature of the pellet. As that these 2 points is difficult to measure. We can't insert the K-type thermocouple to change the physical geometry. Therefore, we need to find this one TH and TC so that we can get TCS and THS in the final form. This part is already in the literature where they are doing the model for the Peltier model in the thermal domain, and this is the coupling of the electrical domain. I further included the ceramic part, and again this is the electrical model, and further again developed for the desalination system. This is the electrothermal equivalent circuit model, the Peltier model for the desalination system, where you will see that the dotted parts are the thermal node, and this is the Thermion source electrical source model. And the thing is, I need to find a relationship between current and voltage so that I can find the external seabed coefficient and the resistance of the Peltier module to measure the surface temperature. Again, now coming to the how I'm starting with the model, the thermal modeling. This is the heat transfer equation for the Peltier module, and this is for the again for the cold ceramic surface. This is one where the first term is explaining the thermal conduction. Second term is explaining the Peltier effect, and third term is about the Joule heating happening inside this. Again, this equation we can visualize the Fourier transform with the heat conduction equation at the evaporation section, this section, and this equation is representing this thermal node, and this equation again representing this equation node, which is for the condensation chamber happening, steam condensation happening here. But the thing is, these two equations and these two equations are equal. Now, the thing is that we have to find the essence of modeling is to find the difference in temperature of the Peltier module. Now, the thing is to what to find, how to find the things that if you see these equations and if you addition and subtract this equation, you'll get TH plus TC and TH minus TC. And if you add again this, we can get the TH and TC part. Therefore, this was the final expression which I am getting for the internal temperature difference. But what this expression explains? What are the physical significance which draw from this is the first is the thermal network of the ceramic surface, second is for aluminum network, and third is the heat generation due to the Joule setting effect, and fourth is about the Peltier effect because considering the aluminum plate, and fifth is the due to the load current to the ceramic surface. The thing is, if you want to have an open circuit condition, if I put I equals to 0, I can get this kind of things, and this will give me the initial conditions. The thing is, if I find this at TH minus TC internal temperature difference, then what's next? Because I need to have modeling in the loading condition. Therefore, need to find the variation of internal temperature with the load current. Since the equation was very large, I just put in the small format where PQRST is representing these two equations are similar. And when I differentiate this, I am getting at this equation considering the practical value of the thermophysical parameter and operating condition. This is the thermophysical parameter, which is the Seebeck coefficient, internal Peltier resistance, and the thermal conductivity. And the operating condition is I'm just taking for the desalination. As for India, it is at 920 meters height when I'm in the Bangalore. Therefore, the desalination is happening at 97.6 degrees Celsius. Therefore, I consider 370 Kelvin for the operating range. And again, if when we are differentiating this part, so many coefficient will come, PQ, all those things, and I need to neglect the things to derive from to coming to this part. And when I come to the internal temperature difference is coming like this. This is the third order system. To analyze the third order system is very difficult. Therefore, again, I further what I did is I compare the S and T. If you see the term S and T, you can easily neglect the term S with the T. If you see this term, this is the slope of the Peltier module, which is independent of the load current. Here is not a multiplication of the current. And we are getting an internal temperature difference as a linear function of the load current, which is I can easily plot and analyze the things. The discussion comes means finally I need to have this voltage parameter so that I can practically measure it, and from this voltage parameter I can define this effective Seebeck coefficient and effective resistance, so that again this coupled temperature difference I can get from the electrical parameter. So if you do the circuit analysis for that, this is the voltage we are going across the terminal, which is the current flowing through this. And when I derive all those things, this is the voltage term coming. If you see first term and this term, you can see that Rm can be extracted with this term. Therefore, we can derive this parameter. Again, if we go for the other without heat sink, means without considering the upper part of the heat sink, I'm getting this thermoelectrical parameter like this. And here again, derive everything where I'm getting a voltage like this. Voltage expression is like this. And again, I will compare this term with the previous equation was I will get a Peltier resistance like this and the Seebeck coefficient like this, which all are in the measurable parameters. If you put the value, we can get the things. This is the IV characteristics of the Peltier model. From this IV characteristics, I need to extract the Seebeck coefficient. From there, that I can derive the dt by di, that is the slope of the temperature difference. When I derive this one is coming here, internal temperature difference is like this, where okay, where the internal temperature difference slope is coming, sorry, is coming 0.8 degrees Celsius. And again, based on that, what I derived, I just follow the things and I get the Seebeck coefficient and the Peltier resistance. If you see this dotted line was developed for the external things, and it is this dotted lines compared to this solid line for the Seebeck coefficient is intuitive, and from the intuitiveness you can directly see that the result is pretty good and sure. And for the same thing for the resistance measurement of the Peltier module, this curve is coming because if there is more resistance, voltage drop will be more. Then this dotted line, which is for the intrinsic, will be should be lower compared to the extracted uh, external resistance kind of things. This is the things which I already explained, and based on that, for the future outlook, means I was developing my own setup for proving the things because at the modeling I did, after it I need to prove it with the expert experimentally whether the what I did is correct or not. And this is the hybrid source desalination system which I developed for the prototype scale. Where for second is so actually I need 4 temperature sensors for the measurement, and I myself developed a custom made temperature sensing board so that I can log in the data and again compare with the what's happening inside. Again, the last part comes that manufacturer is not revealing the material characteristics of the Peltier module. You don't know what's happening, what is the material inside the Peltier module. Either it is bismuth telluride, either it is scandium diffusion, or either is antimony. What I did EDX, energy dispersion X-ray spectroscopy, after breaking the Peltier module. When I break the Peltier module, one I'm using 2-3 Peltier models from manufacturer. I'm just getting one is having a bismuth telluride antimony and bismuth telluride for the second one, and both these two are in the research work. They have IV characteristics. If we have IV characteristics for both of them, then I can again with the IV characteristics I can develop the internal temperature difference, and from the internal temperature difference I can extract the external Seebeck coefficient, and after developing the external Seebeck coefficient I can measure the temperature difference and surface temperature measurement. In a conclusion, I successfully integrate a Peltier model into hybrid source thermal desalination system to enable precise surface temperature measurement. And analytical model I developed again with the load current. Beauty of this modeling is to find the initial condition which I saw. Because of this initial condition, accuracy under loading is very high. Because if this kind of things again you can develop with the thermal network, but to find at the initial condition what happening also I need to have an initial condition which I developed this. Another thing is that beauty is that I'm measuring the things simultaneously, this surface temperature and loading the power also, means if you give the temperature difference to a Peltier model, I'm generating the voltage also at the same time. This is the beauty for this model, and this model allow us to estimate the extrinsic parameter of the Peltier module, especially Seebeck coefficient and resistance under the operation condition. And to validate the analytical findings, a hardware evaluation setup is designed as I have shown in the previous setup. These are the reference. Thank you.
So much.
Before going ahead, I just have one clear. In the previous talk, somebody asked about this one thermal desalination system. Why it is not is in the large scale kind of things. The reason is about as Professor B has explained that because of the latent heat and this large amount of latent heat is going to be wasted and we are not utilizing that. That's why it's concentrated in the small scale. And my work is again about extracting this latent heat again into the system so that efficiency will increase.
Thank you so much. Questions? If not, the next paper
Yeah.
is out at the same time.
Yeah.
No problem. I will. Yeah, let's stop sharing.